It's my pleasure. Good evening or good afternoon, depending where you are. It's my pleasure to introduce Yves André from Paris Sorbonne and CNRS. André is our speaker today, and Yves will talk about one or two remarks on the Tate conjecture. Please go ahead.
Thank you very much. Thank you for the invitations. This talk is about, it's a remark about a remark, in fact, on the Tate conjecture. The Tate conjecture is a very old conjecture from the 60s, dealing about the relation between algebraic geometry, the algebraic cycles, and étale cohomology. So étale cohomology was devised by the creation of Grothendieck. It's a new cohomology created by Grothendieck, which is purely algebraic and which works in any characteristic for any algebraic variety over any characteristic. The very interesting thing about it is that if you take a variety over a field and look at the étale cohomology of it, but not of this variety, but this variety over the separable closure of this field. This is a cohomology with coefficient in L-adic numbers, and it carries an action of Galois. So Galois action, which is extremely important in arithmetic geometry, because out of it, this is much connected to the lambda program. You can connection with automorphic forms and so on. So it's that's a major role. And the Tate conjecture is to understand, specifically, the invariant, the Galois invariant, which is a very natural question. The Galois invariant in this cohomology. What is the meaning of the Galois invariant? And the conjecture, so the main part of the conjecture says that this Galois invariant should correspond to classes of algebraic cycles. So that's the philosophy of the subject. And of course, this is completely open, except in some very special cases. But recently, 3 years ago, Ben Morden published a very interesting remark on the Tate conjecture, which linked, in fact, two parts of the Tate conjecture, the part which I just described, and another part which is about the semi-simplicity of the Galois representation provided by étale cohomology. So let me be more, I'm sorry, okay, more specific. So the setting is that we start with a finitely generated field, which means a field which is finitely generated over its prime field. For instance, a number field, or finite field, or something finitely generated over those two kinds of fields. Ks is a separable closure, and Gk denotes the absolute Galois group. The conjecture is about étale cohomology of smooth projective varieties, K varieties, for K finitely generated field. So let X be such a variety, and bar X denotes the extension of X over separable closure of K. Then the étale cohomology of X, in fact, of bar X with coefficient in QL with a twist, twist is just some cyclotomic action of Galois of Gk. So this is, those space are the representation of Gk which are of interest in arithmetic geometry, which are of utmost importance, including in the field of automorphic forms. Here, the L denotes a prime number, which is different from the characteristic of K. The Tate class is precisely a invariant, a Gk invariant class in this cohomology. In fact, the Tate class occurs only in H2n when you twist cohomology with N. So L will denote by T, so this calligraphic T of X, the set of Tate class in the cohomology of X bar. So this is a QL vector space. And Tate conjecture has two parts. The first part is that the étale cohomology general of any smooth projective variety X is a semi-simple representation, Galois representation. And the second part is about the invariant under Galois. And it says that the cycle class map, which goes from Chow groups, from algebraic cycles on X, tensor QL, to the set of Tate class is surjective. In other words, any Galois invariant in étale cohomology should come from algebraic cycles. So sometimes the first part about semi-simplicity is also attributed to Botanic set. So, an equivalent form, this part, this S of X, can be formulated in the following way, in a group theoretic manner, in the following way, that the Zariski closure, which I denote by HL in also talk, of the image of Galois in this Galois representation given by étale cohomology of X is reductive. So there are two parts, and they look very independent, in fact. So, okay, and this theorem by Monen, which is 3 years old, says the following. This is only in characteristic 0. It says that, in fact, T implies S. More specifically, if you assume that T of X for all X over all finite extension of K, then you have S of X for all such X. So the first aim of this talk is to advertise this theorem, to explain it, to refine it, and to give an unconditional formulation in the framework of observability theory. Further, to discuss the case of positive characteristic, which is not included in this. So, but I mentioned observability, so let me say a few words about this theory, which belongs to the theory of linear algebraic groups, which is maybe not so well known. In fact, I know people who are very competent, work in these linear algebraic groups, and didn't know, in fact, about this observability theory. So let me say a few words. This is very simple. So let G be a linear algebraic group over a field, let's say, of characteristic 0 for simplicity. Field F of characteristic 0. And let H in X be a closed linear algebraic subgroup. I will speak about representation of H or representation of G, and by this I mean finite dimensional rational F linear representations, algebraic representations. So the definition of observability, which is due to Pianelli, Borula, Hochschild, and Osto in the 70s, is that the subgroup H is said to be observable in G if every representation of H is contained in a representation of G. Now, the main theorem of the theory is list of equivalent criteria. So there are a lot of authors, and so the first condition is that H is observable in G. Second condition is that every character of H occurs in a representation of G, which is a special case of A, of 1. It means that one-dimensional representation of H occurs, so it's contained in representation of G. The third point is seems even weaker. It says that for every character of H, which occurs in a representation of G, its inverse also occurs in a representation of G. In other words, it's weaker than 2. It says that every one-dimensional representation of H, which is a quotient of representation of G, in fact, occurs is a sub-representation of occurs so in a representation of G. The fourth condition is of different nature. Says that H is in fact the isotropy group of some element in some representation of G. This is very reminiscent of the Chevalet famous theorem, which says that any closed subgroup H of G is the stabilizer of a line in some representation of G. But here it's not about stabilizer of lines, it's stabilizer of elements. It's stronger. And the fifth condition, which is completely geometric, says that the conditions H is observable in G is equivalent to the quotient variety G over H is quasi-affine, which means open in some affine F variety. So now let me discuss some examples and counterexamples. First counterexample is a Borel subgroup in a reductive group of positive dimension. This is not observable, for instance, by the fifth criterion. The quotient is projective, so it's not quasi-affine. For instance, the standard S2 representation, dimension 2V, becomes, if you restrict it to the Borel, an extension of one character by the inverse of this character. The first one is not contained in a SA2 representation. So it's not observable. On the positive side, example, any normal subgroup is observable. In fact, conversely, if H is observable in G, and if moreover for any G representation V, the H invariant in V is a G stable space, then H is normal in G. This is a criterion due to Edo, I, and Sun. What matters for the sequel is the special case, in fact, is the following very important property. That if H is observable in G, and if for any G representation V, the H invariant in V and the G invariance in V are the same, then H equals G. In fact, this is the reason for the name observable. It means that you can observe the subgroup H by looking at the invariance. So from the viewpoint of invariant theory, this is a very important criterion. And for instance, if you consider the previous counterexample, the Borel in a reductive group satisfies the property that for any G representation V, H invariant are the G invariant. The Borel is not observable, and of course, H is different from G. So since it's very important for the following, let me give a Tanaka proof of this observation, which is very simple. So the fact that for any G representation V, the H invariance and the V invariance coincide means exactly that the functor from the category of G representation, H representation is faithful. But the condition that H is observable means that for any H representation W, any H representation W is contained in the G representation V, and also dually, it is a quotient of a G representation V dash. So that by full faithfulness, the composition is a dimorphism. Thus, V, the image, is a G representation. Hence, the functor is essentially surjective. Another nice thing about observability is that it is insensitive to passing to connected component of the units. So now, let me take the main result of this talk. Coming back to the geometric setting of algebraic variety X, which is projective and smooth, of a field K, which is finitely generated, this prime field. We have étal cohomology of X bar with coefficient QL, L different from P, and it is endowed with a Galois action, and I denote by HL the Zariski closure of the image of decay in the group of linear transformation of étal cohomology, which I denote by GL. The main theorem is that this Zariski closure of Galois is always observable in GL. So let me sketch the proof. First, so one has to separate the two cases, characteristic 0 and characteristic P. In characteristic 0, there is first a reduction to the case when the base field is a field of rational numbers, first by a specialization argument, which is rather standard and due to Serre basically, and it uses a Eiffel argument, the number of fields are Hilbertian, reduced to the case where X is in fact defined over a number field. Then to pass from number to Q, we consider X as a Q scheme, restriction of scalars, and as such I denote it by X dash. Okay, thank you. So anyway, there's a small, let's keep this, there is a small argument based on the fact that, in fact, observability is insensitive to passing to connect component and some induction argument, which allows to reduce to the case where the base. Okay. Okay, so now it's Monod's argument. So I will use the third criterion for observability, which says that when you have a character, you know that it occurs in a representation, a character of H, you know that it occurs in representation of G, then if its inverse also comes from representation of G, then H is observable. So now H is not any abstract algebraic subgroup. This is the image of Galois in G, which is linear automorphism of étal cohomology of some algebraic variety. So I assume that this character of HL is contained in a representation which I call V of GL. Such a representation comes from a character of GQ. Now we are over the base Q, the base field Q, with value in ZL cross, because there is an integral structure in étal cohomology. It's not only with coefficient in QL, but it's come from, that's also defined an étal cohomology with coefficient in ZL. So the claim is that the restriction of this character to an open subgroup of GQ is in fact an integral power of the cyclotomic character. Of course, we may assume that the character is infinite, otherwise this is trivial. And the first ingredient in the proof, so this is Monod's argument, is Kronecker-Weber, which describes all the abelian extension of Q. It's all cyclotomic, basically. And so the tension Q, which corresponds exactly to the kernel of this character, contains the cyclotomic ZL extension with finite index. But L is totally ramified in this cyclotomic ZL extension. So the inertia group at some prime above L is an open subgroup of the Galois group of L over Q, which is an infinite extension. The second argument, which comes from periodic Hodge theory, in fact, P is L in this case, is that V is of geometric origin, hence it is Hodge state. And so is its restriction to chi, so one-dimensional subspace. And there is, because it's Hodge state, it's easy to subset J of I, which is it's open, it's a Galois group of L of Q. So that the restriction of chi to J is an integral power of the cyclotomic character. The conclusion of this is that chi is in fact potentially means up to a finite character of finite order, if you want. It's potentially a Tate twist. But if it is so is its inverse, in fact, which just to extend the representation of GL. So this concludes the fact that HL is observable as the third criterion of observability. And in fact, one sees that any character of HL is potentially a Tate twist by the second criterion. Not that the reduction to Q is completely essential to this argument, because if you take an elliptic curve with complex multiplication, in which L splits in the field of complex multiplication, then the H1 of X bar with coefficient in QL is the direct sum of two characters, which are not at all potentially Tate twist. So now let's consider characteristic case and start with the case when K is finite. In this case, we have a functional equation for the zeta function, which shows that so character is just a story in this case of an eigenvector Frobenius acting on the étale cohomology. And if alpha is a Frobenius eigenvalue, because of the functional equation for the zeta function, for some Q, for some n, I'm sorry, Q to the n divided by alpha is again a Frobenius eigenvalue. So that up to this Qn, which is a Tate twist, the inverse of your character is again a character which occurs in a representation of GL. So this settles the case of finite fields. Now, if K has transcendence degree, positive transcendence degree, a specialization argument, à la serre, as before, using this time that function fields are Hilbertian, reduced to the case of transcendence degree 1. And as before, we reduce to the case from number field to Q, we can reduce from function field transcendence degree 1 to the case of the rational function field. T. Now, one can try to imitate Monen's argument by replacing Kronecker-Weber by its analog in characteristic P, which is Hayes' theorem. I'm not sure how to pronounce his name, but which describes abelian extension of this field of a rational function over Fp. And the result is that there are compositions of two kinds of extension. The first are the Karlitz cyclotomic extensions, which are associated to every close point of the projective line over Fp. And the second kind, which is much obvious, the extension of K which come from extension of FQ itself. So, but Carly's dichotomic extension are infinite cyclic, are well studied, and one knows that they have infinite well ramification at a suitable time. But in our case, because P is different from L, the Galois group of L over Q, over K, I'm sorry, which is contained in ZL cross, is potentially cyclic and tamely ramified everywhere. So this rules out the first kind of extension, or at least if they are infinite. So L comes potentially from an extension from FQ. And by suitable specialization to T of the variable T, when reduced to the case when K is finite. Maybe just a word about this Carly's cyclotomic extension, which are maybe not so well known. They are constructed as follows. They are complete analog cyclotomic extension in P. There's first this famous Carly's representation of the ring FQ of T, the Q missing there, as a field of endomorphism of the algebraic closure of K as an additive group. And for any P in FQ of T, one associates some additive polynomials, which are a separable polynomial P tilde, which has coefficient in FQ of T. And the roots of this polynomial, F tilde, which are the P torsion points of K bar, gives the abelian extension, an abelian extension of K. In fact, one could take a different route to reduce to the case where K is finite, just by spreading out. One can view K as a function field, because it is finitely generated, of some variety S over FQ, and X as the generic fiber of some family over S, and use the fact that characters of geometric monodromy are finite, in fact due to the linear. So this alternative proof. Now the corollary, which improves Monon theorem, we come back to characteristic 0, is that if you have for specific X over K, the property is the first part of the second part of Tate conjecture, T of Xn for all n, then you have the semi-simplicity of étale cohomology of X. So this is an improvement because you don't speak about all varieties X at the same time. So there's only all the powers of a specific X, and this can be checked in some cases. So this becomes sort of useful results. So the proof goes as follows. We are in characteristic 0. We have a Tanakian semi-simple tensor category of pure motifs with coefficient in QL set, which is defined equivalently using motivated cycles, which introduced long ago, or using Norris construction. This gives the step. And in particular, we have Tanakian groups, motivic Galois group attached to X. This is a reductive subgroup because this category is semi-simple, which are denoted by G motivic L X, a subgroup of a group GL. Moreover, the invariance under the motivic Galois group for any representation of GL of the homology consists of motivated classes, which are Tate classes, and which include among them algebraic classes. Conjecturally, all are the same. Therefore, then, we have an inclusion of HL, the image of Galois, in this multi-Galois group, and the conjecture, which says something about the invariance, implies that for any representation V of GL, the HL invariant are the same as the G-motivic invariant. But since HL is observable in GL, it is also observable in the smaller group G-motivic L. And one concludes that XL is G-motivic L. In particular, it is reductive. So this gives semi-simplicity. So in characteristic P, now there is a, well, there is a very recent result by O'Sullivan, which provides a motivic Galois group with similar properties, except that it is not known to be reductive. But it was the main part of the previous argument. So, well, I have another argument, but since it's a bit technical and since, fortunately, I've lost a lot of time with connection problem, I will maybe skip this technical part and come to another remarks about the Tate conjecture, which is not related to this story. So this is in fact a remark I made long ago, but which is maybe not so now K is a number field. So I choose an embedding into C, and I denote by bar its algebraic closure in C. X over K is, as before, a projective smooth variety. Before I spoke about étale cohomology, but now I will speak about two further cohomologies. Betty cohomology, which is the usual cohomology, singular cohomology of X, the complex point of S, denoted by X, H Betty of X. And there is the algebraic de Rham cohomology of X, which was considered first by Grothendieck, I think, and which consists of a differential form. So it's built out of differential form, algebraic differential forms, de Rham complex. And those two cohomologies are related by a period isomorphism, which is more or less just integration of form along cycles. This period isomorphism, by pi, so Greek pi, is between the Rham cohomology, which is here a K vector space, so I twist, this is not important, tensor C, with the Betty cohomology, which is Q vector space, tensor C. By analogy with Tate classes, I define a Grothendieck class, this is not a standard terminology, as a class psi in de Rham cohomology, so the K space, so that its image by the period isomorphism is in the rational Betty cohomology, without tensoring with C. So there is a double rationality of a K on the left-hand side and of a Q on the right-hand side. I did not by this G star X, a set of Grothendieck classes. This is a Q vector space. And the weak form of a period conjecture, I did not by G of X, is that the cycle class map, this goes from the Chow group of X, algebraic cycle, to Grothendieck classes, is surjective. So anytime you have a class which is rational in de Rham cohomology and also in Betty cohomology, with respect to the comparison isomorphism, this class should be algebraic. The stronger form of this conjecture is that the transcendence degree over Q of the periods of X, the period of X are just the coefficient of the matrix of this pi, this period isomorphism, when you take basis of de Rham cohomology and Betty cohomology on the other side. So the transcendence degree of the period of X is dimension of the motivic Galois group of X. Now let us consider the periodic case. We have to fix, in addition, an embedding of K bar, Q bar if you like, into QP bar. Then by combining the periodic et al. Comparison theorem with the Artin comparison theorem, periodic et al. Is a comparison between de Rham and et al. Homology, but with coefficient in certain field of periodic periods, which is called B de Rham, which was introduced by Fontaine. Artin comparison theorem is between Betty and et al. Periodic, coefficient in QP. You get an isomorphism, it's a periodic period isomorphism between de Rham cohomology and Betty cohomology with coefficient in B de Rham. It depends on IP. And one can define similarly the Q space of periodic Grothendieck classes G, IP, X. So there was an old question by Fontaine when he asked it in 88, I think, or early 89, is the following true? So the periodic analog of Grothendieck's weak period conjecture is a cycle class map from a group to these periodic Grothendieck classes surjective. In other words, whenever you have a rational class in de Rham cohomology and a rational class in Betty cohomology, which match through the periodic isomorphism comparison theorem, then does this class come from an algebraic cycle? In stronger form, the question is whether the transcendence degree over Q of the IP periods of X is the dimension of the motivic Galois group. So just a periodic analog. So my answer, which takes back long ago, is that this depends on IP, on the choice of IP. For instance, if P is 11 and X is a modular curve of level 11, then there are two different embeddings of Q bar in QP bar, which are denoted by IP and IP dash, for which in one case, the transcendence degree of the periodic period is 4, which is the dimension of the motivic Galois group. And in the second case, this is less than 3. The proof realizes the fact that this, in fact, this modular curve, QP is a Tate curve, and one knows the image of Galois cells. So after I told this to Fontaine, I remember I called him 1 hour long from Max Planck Institute. He was very disappointed. But he suggested, but if one considers a very general IP, what happens? Then the proposition assumes that IP is sufficiently general. Then the Tate conjecture for X, for the all powers of X, imply this periodic analog Grothendieck conjecture, even in the strong form for all n. In fact, here there is a small clash of notation because Tate conjecture was L-adic coefficient, and now it passed to P-adic coefficient because traditionally one said P-adic Hodge theory and not L-adic Hodge theory. So, okay. Well, so the idea is that, in fact, it's very simple. We have a period torsor called P of X, which is a torsor under the motivic Galois group. And this periodic isomorphism, this comparison theorem, periodic period maps, defines a B de Rham point P of X. And the issue is whether this point is generic or not. And one can study the behavior of this point when one changes IP by twisting by an element of GK. And in fact, under the Tate conjecture, since you know that the image of GK is very big, is dense in the multilegal group, one can modify this IP by a general element such that in order to achieve the conjecture, so the fact that this Bedouin point is generic. So maybe I better stop there before the connection stops again. So thank you very much.
Okay, thank
you.
Yes.
Thank you, Yves. Very nice talk. By the way, I didn't receive your slides at all, so the communication is not at all. Anyway, are there any questions or comments on the talk?
Well, I think there is a relation between the second part of your talk and what Kontsevich was trying to explain on the last Wednesday, which is 2 days ago, because he was trying to precisely use non-commutative geometry in order to define, to replace, if you want, the period map and the Betti cohomology using the quantized calculus. Now, we were very confused in what he said, because, I mean, it was quite confusing. On the other hand, okay, I'm sure it will have a bearing on the second part of your talk. I mean, the part which is related to this Grothendieck conjecture on the period map and so on. So that's something to think about. But on the other hand, okay, it would take a lot of work to explain what he was trying to say, which we didn't quite understand. I mean, to be honest, I mean, but no, I mean, what is the relation also? Is there any direct relation with the Hodge conjecture, or?
Well, in fact, there are parallel conjecture. You see, if you can reformulate this conjecture, the weak Grothendieck conjecture, the Hodge conjecture, the Tate conjecture, and even some other conjecture, as a faithfulness conjecture for some enriched realizations, starting from motives and going to some kind of realizations for the Hodge conjecture. It's just the target is the Hodge structure, for Tate representation. So, but there is no direct relation.
There is no direct relation. No.
Very strange. No, there is no direct relation.
No, I mean,
this is what is interesting is that even with the Grothendieck conjecture, there is no direct relation. This is the third parallel conjecture, faithfulness conjecture. What is interesting is that in this periodic case, there is a direct connection between the periodic Tate conjecture and the periodic Grothendieck conjecture. And this is the only
it is the only place
direct relation that I know between two such kind of conjecture.
I understand, yes. Yeah, no, I think if you want, the idea of Kontsevich was, okay, since we know that in the non-commutative world, the RAM theory is replaced by cyclic homology, and we also know that it pairs with the quantized calculus, then he was sort of extending, if you want, the period map and all that in the non-commutative framework. And he was giving some very interesting examples, but we couldn't really keep track of what he had in mind. I mean, I don't know, Masoud, did you?
Yeah, well, what I noticed also indeed, as you said, Alan, I think he also had this torsor. I mean, he came up with the torsor, which is kind of interesting. But I was wondering if one could maybe look at some subset of pairings he was doing and hopefully define something like a monodromy group or something. As a small part. And then if you show that it is closed under this co-multiplication, I mean, he had a triple co-multiplication, then this would be some sign of a group structure, quantum group structure there. But
but what I wanted to say simply is that, in some sense, what he was doing was extending this type of discussion with the period maps and all that in the non-commutative framework, and this seems to be a natural way to do it. I mean, but we cannot claim that we understood what he was doing. I mean, no, here, okay, we understand, but I mean, these problems. What seemed to be also very interesting was the role of Biederam in the isomorphism, because we have with Katia, we have an analog of Biederam at the Archimedean place. It would be nice to know if it could play a similar role as in what you were explaining, but okay, this is far-fetched. I mean, you know, really, I mean, it's.
But is your Biederam kind of field of periods?
Yeah, well,
by field of periods, I mean something.
Yeah, well, you see.
Homology.
Yeah, well, the way it enters, if you want, it declares that in fact we don't have the correct Galois group, of course, for the Archimedean place. I mean, because the Galois group should be for the reals, it should be R plus star, and so it uses that. If you want, it uses the fact that it should be the veil group, not Z mod 2Z, and so on. So I mean, this is what it achieves essentially. I mean, to give the natural Galois group at the Archimedean places, so that, for instance, you would have the class field isomorphism with the ideal class group. That's what it does. So, but I don't know in which sense, you know, it could be used. I mean, it all ties up, you know, with this paper of Veil in Toku, where he was dreaming about some Galois theory for that would fit with class field theory isomorphism. But I don't know if it could play a role here. I have really no idea.
Could one formulate? Sorry, could one formulate a kind of Tate conjecture for your theory, Alan? In that case,
well, I don't know. I don't know. I don't have enough feeling, if you want, yet for this stuff. I mean, what we did with Katia was so parallel to the construction of Fontaine that it was very convincing from this standpoint, because it was an exact parallel. And then, you know, I mean, okay, it was found in another guise by Scholz and Clausen in what they were doing, but they were obtaining the same thing in a different presentation, but they obtained the same thing. So it must have something in it, but okay, more than that I cannot say. I mean, you know, I cannot say that I followed, because okay, we had this problem also with the communication, so it was very difficult to follow your talk, Yves. I mean, you know, I could follow the main points, but then it was quite difficult to follow the process. I mean, I think I understood the main points, but yeah. Well, you know, it came from well, the subject is quite difficult, of course. Yeah.
Any more comments?
The was to make Mona's Anthony by formulating it in terms of observability theory. So then you get not an exegesis of conjecture, one conjecture implies the other, one an inaccessible conjecture implies the other, but the theorem. That's the main point.
No, but this notion of observability is a very nice notion. So this, I mean, the fact that you have the equivalence with the invertibility of characters this is quite remarkable. Because I mean, invertibility of characters, it looks like, okay, I mean, you know, it's not much to ask. I mean, but it seems, and it seems a very powerful way to prove that something is observable. So that was very striking. Yes, certainly.
Yeah. Also, this surjectivity and injectivity reminds me of Bonkan. I don't know why.
Well, okay. Yeah. Well, I don't know. I don't know. Yeah.
Any more questions or comments? Maybe Oh, maybe the slides have arrived now. If we have, no, not arrived. If we have your agreement, if maybe we could show the slides on the web page. You have can we eventually put the slides of your talk on the web page? Hello?
Yes, maybe I can send you. Maybe I can send you later.
Yes,
later
definitely.
next
Yes.
week.
Yes.
Mhm.